hardware here. Hopefully that's okay. Yes. Injection molding. These are the topics we will cover today. If you know all of them, you are free to leave and everyone is happy. Otherwise, we can talk about them. Let's talk about them. Yeah. Can you see all of this, by the way? Is it legible?
Yeah.
Barely? Yeah. That's quite a list. I think we should just go through it by bit. And you should know, like, by the time we're done with this lecture and done with this course, you should be sort of on a first name basis of all of these topics, right? You know drafts already, right? Making ice cubes. Sink marks, you don't know that. Thickness of the let's just go through it, okay? If anything, you can always like jump to the handbook. It's all written down there. I've also got a copy of a previous lecture in the handbook with really bad sound, which is why I got the mic now. But I'll let you. It's also linked to that from the course website. All good?
Yeah.
Yes, let's continue. Let's talk about the first thing, drafts. You can see drafts quite clearly on this charger, like where the two halves meet, right? So there's the top bit and there's the bottom bit. And that wall is certainly not 90 degrees towards that surface. It has like this flaring angle like that. Why is that? Yeah?
The piece from the mold?
Yes, to get it out of the mold. So when we make stuff, like everything that looks vertical is in fact not vertical. It's always drafted unless you do some tricks with the injection molding tool. Like you can see it very clearly on this part. It's drafted like that on the outside and like this on the inside. I can sort of try and illustrate also why. So typically 1 to 2 degrees. If you have a rough surface, like if you have a surface texture like this, has a texture on it on the outside, it's polished on the inside. You can sort of hear the difference. If that texture is rough, you need more draft because otherwise it's going to stick. It's like sanding paper. If you got ribs, like small details, they can be close to zero. Like we always have this problem with the ribs that we want them narrow, not to make sink marks, which we'll talk about later. But if they're very narrow at the base, then and you have a draft on it, it goes into nothing at the top. So typically you draft gussets or ribs less than you draft walls. Round holes can sometimes have zero drafts, like holes that go through the thing. Yeah, and drafts and gussets can lead to thick corners at the bottom. Let's talk about this. Seems to be working, yeah. So imagine we make ice cubes. Let's do the mold first. The mold could be blue, right? So we have like, that's the top of the mold, and that's the bottom of the mold. I just made this upside down, sorry about that. Let me just flip it. Let's start with the ice cube example and then we can do something else afterwards, right? And then the ice cube is in here. Right? That's our ice cube. Yes. And this will come out of the mold just nicely because that wall has an angle, right? This is, I don't know, let's say it's 91 degrees, right? So far, so good, okay? Let's say that, let's say we make a part with a rib. So going back to this, how can I best illustrate this? I'm going to try and make this charger. If you see that from sort of, let me make a section. So I'm going to cut it. I'm just going to take a bandsaw and cut it like straight over here. So then that charger looks something like this, right? Goes up, goes down, and to the other side. Right? So that's my charger, just a section of it, right? And since I've been very careful with my drafts, I have drafts on like all of these sides are drafted. There are no vertical walls here. It's either like tilting this way or the other, right? Because otherwise I won't be able to get it out of the mold. Right? So that's like the essence of drafts. You get that, right? Next, if I do a gusset, so now I'm going to do a section and try and bear with me. Let's say I have, I got the base of this. And then I got the wall. And then I got these little ribs that are around here. I'm just going to look straight at the rib, and that rib is going to look something like this because of the draft. It's going to look something like this. Does that make sense? So sort of this is the floor, that's my rib section of it, and that's the top edge I'm looking at into the wall. Is that okay? Yeah. So what I talked about here is that this base will be very thick if you got a big draft here. Let's say that this is 92 degrees, right? That means you get this very big area of plastic, and that is not good. Why is that not good? Okay, I'm going to go back to my next slide and tell you why that's not good. The reason is that plastic shrinks. So typically, plastic shrinks about 1 to 1.5% when it cools down, right? So that means, going back to this, if I have this big rib going up here, I got a bunch of plastic in this area, right? So what's going to happen is that my surface is going to get like that kind of a shape because there's more plastic here shrinking than anywhere else, right? And that's called a sink mark. And sink marks, you can see it on this part. Let's see. Sink marks are not the end of the world. It's like there's a difference between something that needs to look nice and something that's just functional. Most cows don't complain about sink marks. So we let ourselves do quite a bit of sink marks on this thing. If you look here, you can see there are inserts like little metal things. Next to the metal thing, we have a lot of material like up in this area. So if you look like carefully on this top surface, like here and here, you can see the, sort of the surface is not even, it dips down a bit. You can pass that around, you can see it. So you have 4 very visible sink marks on the top there. Again, sink marks, it's not a big deal if you make something that's technical or not visible, but it is a big deal if you make something that's visible, okay? So we want to avoid sink marks. How do we avoid sink marks?
Just make the thing a little bit smaller.
Yes?
And the less plastic, the less it will retract.
That's a good point. How much smaller?
It depends the height
Yep.
of this part.
Yes?
If it's small, we can make it at with an angle of 90 degrees.
Yeah. So let's say I got this rib, right? It's now, let's do it like, it's half a degree of draft. Like you can barely see it. Actually that's 0, but let's imagine this is half a degree of draft, right? And then there is a rule of thumb. I love rules of thumb because you don't have to like calculate, you just need to sort of look at it and it looks right. If this is 1, let's say the thickness is 1, right? That's a 1. Let me just put a marker on it. Like, if that's 1, if this is 2/3, you're home free. 2/3. Okay? So if that rib is 2/3 of that thickness, you're not gonna get like any major sink marks. Okay? So that means if this wall, let's say that wall is 1.8 millimeters, which is like quite bulky for a headset, but let's say it's that. If this rib is 1.2 at the base, that's probably okay. Okay? It should not be anything more than 1.2 because then you will start seeing like visible indents at the base. Okay, so that's a sink mark. You will find sink marks on virtually any product if you just look for it. Typically, polished surfaces are less forgiving in terms of sink marks. So if you take something that's high gloss, like plastic, and you sort of hold it up to the light, you can see the sink marks quite easily. Which also brings us to the second trick. If something is not polished, if you make something with a surface grain on it, that hides the sink marks. So if you got something that has marks on it and you just want to hide the ugliness, put some grain on it. The marks will still be there, but it's going to be a lot more difficult to discover them. Okay? Yeah. Yeah, last but not least, you often have this trade-off between having sink marks on something and having a strong part. So going back to this, let's say this is a wall and here's a little arm or thingy that sticks out, right? Of course, let's say I'm going to put a load on this, like F, big force coming in, right? Of course, I want this arm to be as thick as possible to take up that load, right? But if this is too thick, then I'm going to get a sink mark down here, right? Also, there's another thing I would normally do if I have ribs like this and I want them to be super strong. I add a little fillet at the bottom. Actually, I add a big fillet at the bottom. This is like really clever because it makes it so much solid at the base, right? So that's a strong rib, right? It's got big fillets, it's got a big cross section, right? But doing this also means that if I make a circle inside of here, sort of illustrating the bulk of material that needs to cool down, that's a lot of material that needs to cool down because of my fillets and because of my thickness, right? So that means I get a lot of sink in this part, right? So that's sort of the trade-off I need to be doing. Just keep in mind that there are trade-offs between sink marks and making something that's strong. And if you're really clever, you'll be able to make something that's strong without the sink marks. That's sort of the trick here. Okay, so far so good? Yeah. Also, different materials shrink differently. 3D prints will not show you sink marks because that's a completely different process. So don't be... you should expect where to see sink marks. Like you're not going to see them from your prints until you get into production. So you need to sort of know what to expect. An SLS or a silicone casting or anything else, they're not going to give you clues as to how your final part's going to look. So just keep that in mind when you order prints and prototypes. Sink marks is something that you only see on parts of tool. Yes. Let's talk thickness. This is probably the thickest part. No, it's one of the thickest parts I made in plastic. The reason it's so thick is that it's going to be like around the neck of an animal of like several hundred kilos. Why do we want to make parts thick? Come on, it's an obvious question. Why do we want to make parts thick?
For the resistance of the part.
Yeah, because it's just going to be like super solid, right? Yeah. Why do we not want to make parts thick? Why aren't every parts in this world like super thick and beefy?
Because it's more heavy, so less practical.
Yeah, it's
more
heavier.
expensive,
Yes.
and it's more difficult to make because you can make a really thick part with the injection molding.
Yeah, you can actually. It's about as difficult. But let's talk about price. Why is it more expensive?
Because you need more prime material.
Yes, you need more material. Yes, good one. Yeah.
Bigger molds.
Sorry.
Bigger molds.
Bigger molds, and there's another factor.
Including the time of the...
Yes. Yes. Now we covered all of it, right? So yeah, first of all, if you make something that's thick, of course it's going to be heavy. Of course it's going to use more material. And when you do injection molding, material is like a big part of the cost. Like your tool is super expensive, but once you get up to volume, it's like the product is virtually only made up of the material cost because you can make a lot of these parts in a minute or in a day. But if you go thicker, that also means you need more cooling time. So you need, instead of like producing like say 5 bits a minute, you need to go down to like 2 bits per minute to allow the thing to cool down before you let it out of the mold, which means you sort of half your production rate, and that means you double your price effectively if you're looking at like the tool hours. Material cost, weight, cycle time. Cycle time is essentially the time it takes to make one of these parts of your production machinery. Thickness, hide sink marks. That's a good one, actually. We didn't talk about that. A nice little trick which you can do, which is a bit dirty, but you can still do it. If you design something like this, and you just don't figure out a way to sort of hide the ugliness, right? Let me just take that out. Yes. So we all agreed this is a bad idea because it gives me sink marks, right? That thickness is about the same as that thickness, right? I can always do this. I could always just like increase the wall size here. Like if I go up to this, I haven't really shown you guys a scale for this, right? If I go up to this is no problem at all, right? Like the circle I get in here and the circle I get in here are about the same size. So the sink is going to be about the same, right? Sometimes you want to just increase your wall thickness just to make something look good or feel more high quality. And just let me know if there are any questions or comments, okay? Yeah. What's undercut? I know it says on there. But let's do it differently. Can you guys show me an examples of undercut in these parts? Let's see. Can I take this apart too? Oh, it's glued. Now we're talking. Yeah, more parts. Undercuts. Anyone want to give it a try? What's an undercut? It's okay to suggest something that's just wrong. No? Okay, I'll show you. Going back to our mold, right? Going back to our ice cubes. Or let's say I want to make this fella, right? We all agree that it looks like that, right? So that's my bottom casing thing, right? And this is all right. It comes straight out of the mold, right? If my mold is here, let's see, that's my parting line. Like my mold can follow, that's not a problem at all. It comes straight out, right? Just like, whoosh. That's not a problem, right? We all agree that's okay. But let's imagine I want some sort of snap detail on this, right? I want this little thing like that, right? Yes, you heard of this before. Yes. So that's a snap, right? And you will see snaps on, where's the main housing? Yeah, there you go. Yes. This has 4 snaps on it. It's like 2 snaps up here and 2 little pockets down here, which I use for holding the front face, which is over, no, can I have the big part? That one, yes. So this has like 4 little hooks on it. Those 4 little hooks go onto these 4 little things, right? But then we go, are we able to take this off? Can you guys try and take off that? Just use like immense amounts of power. You can push. Back here, there's a little hole you can try and push if you find a pencil or something to push it through. Yeah. Yeah. So this is an undercut, right? And the problem with this is that if I don't do anything clever, I'm not going to get this out of the mold, right? Because my mold is going to go right like this, right? And when I start lifting this thing up, it's just going to pull out this little triangle. It's not going to follow in a way, right? That's not going to work. So how do we make details like this? It's okay if it's not doing it. Yeah. So how do we make that little triangle? Because obviously it is possible, right? Maybe we can. It's easier to see on this, I guess. Yeah, this is sort of the same thing. How do we make it? Like, how do we make undercuts? There's a bunch of ways, yeah.
Can create, a part that is moving so you have to
Yes,
cover.
yes, you make a slider.
Yeah.
Yes, you make a slider. And sliders are not super high tech, but they are a bit expensive. Like rule of thumb is like it's $1,000 for a slider. So every undercut is like $1,000. Like rule of thumb again, like depends on a lot of things. But a slider is essentially something that, let's say this is our mold. Looks like that. And then I can have this like, let's see if I can draw this in correctly. I think this will be right. Yes, I think that's right. Hopefully, that's right. Oh, perfect, thanks. Yeah. So imagine our tool looks like this. This is a bit complicated for me also, so bear with me. That's nice, yeah. So what's going to happen now is that, let's see if I am able to animate this thing correctly. I don't think I will, but let's give it a try. So what's going to happen is that I'm going to release my, no, it's not quite doing it. I'm going to release my tool in 2 steps, sort of, right? So first off, I'm going to make this part, that's my slider, this, is going to sort of follow this thing as it comes out. So this thing is stationary. Let's just draw a little anchor on that. That thing's stationary, right? But this thing sort of slides down that way and sort of eases off and lets the part go as it comes out. Okay? I'm going to give that one more attempt because it would look so cool if I got it right. Like that, goes down like this, right? And in the process, since this interface is at an angle, that means, yes, we got it. It starts up here, right? And it comes down like following that face like that, right? And when it's down here, that part is free of that part. And your part can just sort of drop down, right? So that's how sliders work. They just come out, they follow the part out, and as they follow the part out, they sort of go to the side and let it go, okay? You can see sliders quite easily because they are like separate parts in the tool. And because there are separate parts in the tool, you will sort of get you get an edge where the slider meets the rest of the tool. So if you look at this part, you can see that there's a little edge around here that sort of makes up the slider on both sides here. That's really hard to see, but this one is easy to see. You can see here, that's the slider. This is the slider part of the tool, and that's the rest of the tool. You can see this line between it, right? Yeah, just pass it around so people can see. So that's sliders and undercuts, right? Undercuts are totally okay. Of course, there are some limitations here, right? If I do, let's say I'm going back to my U-shaped thingy. That's red, isn't it? It's red. Let's do it in black. Yeah. So if I do my U-shaped thingy like this, like it's very difficult if you have like geometry, which is like, if it's very tight, like this. That's going to be very hard because that slider is going to come down this way and that slider is going to come down that way and they're going to clash and like stuff's going to happen, right? You can do a lot of advanced stuff, but it's more difficult as you do it, right? Just keep in mind, like simple sliders is like fairly easy to do. So yeah, geometry that cannot be pulled straight out is an undercut, right? And it's nice to avoid, but not at all cost. Okay, so here's my next question. So someone tells you to make, let's do this geometry again. But they tell you that they don't want any sliders for some reason. How can I make this without sliders? So what I need that surface. That's surface is super important for me because there's going to be a snap that comes down and it's going to grip onto this surface, right? Like that. So I need that surface to assemble the parts, but I don't want to use a slider.
Can I use the image molding by the
Yes, that's what we did on that part. You can see it, right? Yeah. So if your part does not have to be waterproof or look nice, if it's just like a technical part, it's totally okay to make a big hole. So I can, let's say I make a hole here, right? And then I let the opposite part of the mold make the inside of that snap. Let's do that in blue. So here's my bottom of the mold. It sort of comes up here, and it does that inside and comes down like that. And then I can do my top part in red. Comes up here, and it does the outside. That's a nice little trick, isn't it? Yeah, that makes a snap. If you want to get really nerdy about this, of course, which we should, you should know about your draft angle. We agreed that this could be, well, that's very thin. We agreed that, like, as a general rule of thumb, you can use 1 degree. 1 degree is a nice draft, right? That's sort of our basis. But this area, you got a bit of action going on, because you got the top part of the mold meeting the bottom part of the mold, right? Imagine if there's no draft, it's very likely that it's just going to sort of collide on itself as you close. Like if it's not like super, super precise, it's going to collide, right? And also, if it's very little draft, they're going to be next to each other, but there's not going to be like any pressure, so it's going to leak. So you're going to get like a lot of flesh, like a lot of plastic coming through. So you need more draft in this area. You need 3 degrees in that area. So what you could do, you could do 3 degrees all the way down, but it would also be okay to go 3 degrees down to where these 2 parts don't meet anymore, and then go down to 1 degree. So that could be 1 degree if you're squeezed on space. Okay? So 3 degrees where the 2 halves of the mold meet. And you can see that also on this. You can see that these 2 holes, we did that trick to make these little tabs here. These 2 holes are flaring like a lot. And the reason for that is that we got one piece of the tool coming up like that, one piece coming down like that, and we need that angle to get the pressure between the 2 parts. And that's also why you get this like very flaring hole. But then again, that's not a problem for us. We're just going to cover it with a solar cell anyhow. Okay, everyone gets this? Nice little trick. You should absolutely be doing this if you need snaps on your own products. Yes, clearance is the next thing we're going to talk about. That's something you need to do when you print also. Are you all designing with clearance when you're doing CAD? Okay, I'm going to show you a nice little example. So let's say I design a box for some reason, right? So I'm just going to make. It's going to be a box with a lid. So it's going to be like my lid is here. Actually, it goes the other way. It has a little snap on it. You know what? I'm just going to draw like half of it. But believe me, it's the same on the other side. Okay. So it's going to be this. I'm going to focus on this side now. Come on, do it. So that's my box. That's the top part. And then my bottom part of the box is sort of has the same lip and groove feature, right? That's the little box with the snapping lid, right? Between these 2 parts, you will need clearance, right? Because if you don't have clearance, like if these parts are like dead onto each other, you're not going to be able to assemble it. Oh, let's do that again. Yeah. You cannot design it so that it sort of is squeezed towards each other. You need air between the 2 parts. That's super important. Like everything that's assembled has some level of air between the parts. Okay? So typically you will need, like if you do injection molded stuff, like 0.1 millimeter or the like is often enough to do the trick. I use 0.3 when I print parts because I don't like sanding parts that come out of the printer, right? The reason printed parts need a bit more clearance is that they are quite rough. So, come on, you can do it. Yes. So when the printer works, it does layers, right? So it makes one layer, then the next layer. Well, actually, it doesn't look like that. It looks sort of like this. And then the next layer looks like that. The next layer looks like that. That's not a flat, that side is not flat, right? It's sort of, let's say it's your nominal dimension is perhaps in the middle of this bead sticking out. So you need to pull your walls in a bit to compensate for these rough walls. If you don't do that, you need to spend time sanding off models, and you don't want to spend your time in the workshop sanding models. Yeah. It's easier to take down clearance than to give more clearance after you've gone into tooling. So if I have two parts and they rattle, it's easy for me to sort of tighten up the parts so they don't rattle. But it's very difficult for me to give more space if the parts jam and they don't go together. Why is that? It's going to cost me at least 3 times more to make parts that don't fit than it's going to cost me to make parts rattle to make them stop rattle. Anyone going to give it a try? Why is one modification to the tool so much more expensive than the other? Like typically when you make tooling like this is made in Sweden, but very often it's made in China. And they will give you a price for the tool. And if you need to adjust anything, it's going to be super expensive because they need to take the tool out of production, open it, and then start machining on it, right? But what's more expensive than machining off material of the tool, like imagine if this is undersized, like this rib is too short or too thin or something, right? Remember, this is made in a mold. So if I want to make this rib bigger, I have to remove material from the mold, right? So someone needs to sort of put it in the mill and mill off that piece of material. But if this rib is too big, that means I need to add material to the wall, to the mold, right? So that means that someone will need to take the tool and he will have to weld in or add a little block of material. And that's a lot more complex than it is to just shave off some material off the tool, right? So when you make snaps, like stuff that snaps together, always make your snaps a bit weak so you can shave material off the tool to make your snaps more bigger, right? Don't go the other way. It's a very bad idea to make snaps too powerful and then having to add material to the mold to make them just weak enough. So always make parts, make everything a bit roomy and then tighten up your tolerance by taking material out of the mold, okay? Everyone got that? Yeah. And use clearance when you have two parts. Typically, the way you do this in CAD is that either you just model stuff with an offset, or if you do intersection, like if you take one part, subtract the other, then you just pull the faces a bit off afterwards. So just use like the Q on your keyboard and offset face, just to like offset everything to make that air gap. Super important. It's going to save you a ton of time just to do this right the first time, okay? Do you guys want a break or should we just continue? I've got like 15, 20 minutes. Up to you. It's fine? Yeah?
Shall I leave? I have a supervision meeting.
Yeah, go for it. Yeah, let's talk cost. So, a couple of rules of thumb. More parts is higher cost. Well, that's not well, you expected to see that sort of. So try and integrate as many features as you can into the same part, okay? Injection molding is super in that you can do that. So that also means that if you have the option of doing one part with a couple of undercuts, which means a more expensive tool, that still might be cheaper than doing two separate parts, if that lets you avoid the undercuts, right? So if you got more parts, you got more development, obviously, right? So that you have more like fixing, like every time you do a new revision, you need to update your models, which is going to give you a lot more work. There's more tooling, obviously, like you need more tools. There's more tuning, so if you have snaps that need to fit together or assembly processes, there's more of that. There's more assembly, and there's more risk of error, right? Second thing that drives cost is exotic processes. Like you can do a lot of really cool things with injection molding. And the cooler the things you do, the more expensive your parts. Like if you look at this battery, we've done something called overmolding a couple of places. Like here it's quite easy to see. Like we have this gasket. It's overmolded. So you first make the hard plastic, then you put it into another tool, and you injection mold this rubbery thingy on top. It has rubbery thingies around the battery poles as well. It's a bit hard to see, but you can feel it. So that's overmold, right? You can feel it also. You can have a look, pass it around.
Question
Yeah.
about cost.
Yeah.
It's better to create. Imagine there are two surfaces, plastic surface that has to block something. It's better to add more material and then block the things between these two surfaces, or create holes for screws.
So you have two plastic, so we have two surfaces, right?
Yeah.
And what do you want to do?
I have to block something. For example, I have to block this telephone. It's better to add more material and block it by doing with plastic, or create a panel with a screw. Because
So-
in the first example, you will spend more adding material.
Yeah.
But in the second example, you will spend more creating it.
So when you say block, you sort of you want to take up space to sort of keep your phone in place, right? So it doesn't rattle.
Yeah.
Yeah. So typically, what you do is you don't. When you want to sort of fill up space with something that's plastic, so let's try and draw your example. You got that's your phone, right?
Yeah.
That's sort of your plate. It could just be like, yeah, let's just call it ground, because the other plate is where the action is, right? And this is your other plate, and you want to clamp your phone like that, right? Yeah. So typically the way you do this is that you could just like increase the size of that, but that's generally not a good idea because it's not efficient use of material. So very often, let's try and do this in engineering perspective. I'm just going to draw through lines like that. Yes, is that legible? Yeah. So very often what you'll do is you'll add some sort of ribbing pattern. So that could be like a square set of square ribs, right? So I could do this. I could make a rib like that, and I can make ribs this way. So I sort of get this, yeah, and then the ribs going down. So I sort of, I use ribs to take up that space, right?
So it's better to add material than creating holes and spending.
Yes,
money.
screws are expensive because someone needs to. You need to have the threads. That's expensive. You need to handle the screws in assembly, and that's expensive too. So screws is like one of the things you really want to avoid in assembly. The one thing you really want to avoid is glue. Glue is horrible because glue is messy and it needs to cure a lot of things. But screws is also something that drives cost. So yeah, typically if you can snap something together, that's always better. And also typically assembly is very often a big part of your product cost. So you want to do whatever you can to make assembly easier, even if that means investing more in your tooling or having more expensive parts.
And should it be better to create two plastic molds that can merge together, for example, twisting, they can stick together?
Yeah, that's better than using screws normally. But then you have other factors, right? It's easier to do service on a product with screws, right? So if you're really good at designing, you want to make something that has as few screws as possible, but it's still easy to open and to service, right? I mean, this is a rabbit hole. It's a huge field. It's a lot of fun. But yeah, so we talked about more parts. We don't want to use more parts than we have to. We don't want to use more exotic processes than we have to. One is the process itself involves risk, right? Like if you do overmold, everyone knows how to do an overmold, but like stuff like gas injection or water injection or other things. If you do very specific processes, that also limits your number of suppliers, right? Let's say on a world basis, you have like 1,000 suppliers that can make like these parts. If you require a very specific process, that 1,000 goes down to, let's say, 100, right? So it's a lot more difficult for you to get a nice price if you limit the number of potential suppliers, right? So if you make something that's easy to manufacture, then that will drive your costs down. Yeah. Also, high tolerance requirements means that you have higher costs. Like injection molded parts shrink, right? If you design something that is very sensitive on how they shrink and warp, that means they need to take extra care in production, which means they will have more scrap, more parts that will just be manufactured and off spec, so they will have to sort of recycle them. That's also expensive. So try and make things that's forgiving in assembly. Yeah. Layout. Yeah, as we talked about, assembly is a big part of your cost. So when you make stuff, make a sandwich. And by doing that, I mean that where's the main housing? Yes, that one. Try and make it so that you can sort of, you can place one part and then just sort of stack everything and put the lid on top and your assembly is done. That's a very effective assembly, right? If I need to put something, let's say I need to start working in that direction and then flip it around, work in that direction, flip it around, work in that direction. All of this is overhead, right? That is assembly time, which I use for not doing assembly. I just use it for orienting parts. That's a waste of time. So you want to make a sandwich. You want to make it as easy as possible to just like stack all the parts there and click it together and off you go, right? Blind assemblies. Blind assemblies are assemblies which you cannot really see what you're doing. There is a blind assembly here, and that's the little battery poles in here. Like I sort of need to feel my way to get those in place, and that's not good from an assembly point of view. Like I can fix this with a screwdriver, and it's not that bad, but it's not ideal. You should not make blind assemblies unless you don't really have any options, okay? So blind assembly is stuff that you cannot see. Also, let's say if I had like a circuit board coming up here, and then I would have to have like wires which I would route very neatly so they wouldn't interfere with my circuit board, right? So I would sort of route the wires and then do this. That's also a blind assembly, and you want to avoid those. Yeah, forgiving designs. 3-2-1. Have we talked about 3-2-1? Let's do 3-2-1 really quick. That's a trick from car production, automotive, but it's a nice trick. Let's say I do headphones. So my headphone casing this is my squarish headphone casing of the day. And then I have a PCB. And for some reason, my PCB looks like, maybe there's room for like a speaker, so it's going to look like this, right? So this is my PCB. And we all agreed that plastic shrinks about 1.5 to 2%, right? So that means that this casing, depending on the day and level of humidity, it might be, let's say this is one day, it's 100 millimeters. Another day, it's 99.5. Another day, it's 100.5, right? So if I do screw towers, right? Let's put some screw towers on this thing. I'm just going to use 3. That means that these screw towers will not be spaced evenly. Like that's going to depend on which day I assemble them or which parts I get, right? But I still want to be able to position this PCB very correctly because I got some buttons down here which really need to work. Sort of I got 2 buttons down here like that, and they hit little, yeah. And I got little micro switches down here. So it needs to be correct, right? I want it to be correct. So what I do is I do a trick called 3-2-1. That's a lot of detail. I'm just going to take that off. Yeah. So 3-2-1 is a trick where you say that you have one point of attachment that constrains the part in 3 dimensions. So let's say if I use a screw, that means I use also a screw hole that's sort of a net fit, so it fits like very tightly to the part. And this is going to be my 3. So it's going to constrain in X, in Y, and in Z, okay? It's fixed always on that screw hole, right? My next hole is going to be a slot. So in this PCB, like I make a slot. I don't make a circular hole again, I just make a slot, and then I put a nice little round screw inside of it, right? Now this will constrain my part in Z, and it's going to constrain my part in X, but it's not going to constrain my part in Y, right? So that means that I can, if I fit this first, then this will work like any day, right? And it's going to be super precise because these two, like, they constrain in Y, no, in X, sorry, X. So it cannot rotate, it cannot like sort of rattle around. There's only like one way you can make that fit, right? And then I want to attach the last point here, and that should just be an oversized hole. And this point of attachment, so this is my 2, this is my 1, constrains only in the Z direction, right? So that's how you do a 3-to-1 attachment. Let's say this is a square circuit board. Now I made this odd little shape to get 3 screws in there, but let's say it's a square circuit board. It's perfectly okay to add more screws, but those screws should then be oversized. It's going to be the same thing as this, right? You constrain in your Z direction, right? That's also a 1. So the thing is, this is boss, like that's the boss. And this is sort of your helper. And this is like everything else, right? And this will work any day, and it's going to be super precise. Like if your option here is to make just oversized holes, that PCB is going to rattle, and it's going to be able to play, like end up in different positions every time. But since you're doing 3-to-1, it's going to be like nice and precise every time, and you will also be able to assemble it every time. This is a very nice trick. Everyone should know this. Especially when you do bigger parts, this is very useful. Like circuit board is good for circuit boards. It's also good for like door panels and other things which are big. 3-to-1. Very nice rule. Yeah. Yeah. So make a sandwich. Yeah. No blind assemblies. Forgiving designs. Yeah, also use chamfers and fillets to sort of guide your parts together, right? 90-degree corners tend to snag. If you just round off the corners, you will like snap together very easily. 3-to-1, and use effective fastenings. Like, yeah, we got another presentations on that. But like rule of thumb, don't use glue unless you really have to. Screws are okay service-wise, but they're not as effective as snaps. Snaps is like the gold standard of fastening. But you need to be really good for making like serviceable parts with snaps, but it's still like you should try and get snaps working. Oh, here we got the full list. Yes. Screws are good, snaps are great, glue is expensive, foam tape is a problem solver. Foam tape is like a tape with a bit of foam inside of it, and you use it like everywhere because it's so good. It takes off tolerance. Ultrasonic is a very nice, clever little process that's waterproof. Do you know ultrasonic welding? Let's do that real quick. Yeah, and this is something you see on cheap electronics, and you can also weld plastic if you got like big stuff like water pipes and stuff. That's often welded. But you need to know screws, snaps, and foam tape. It's like on like say headphones. Like very often you will see the battery is attached using foam tape and then just like clamped in place, and the foam tape takes up the tolerance that makes it not rattle. But let's talk ultrasonic welding. Maybe we should do, no, we got 4 more slides. Is it okay? Yeah. Let's talk ultrasonic welding because it's so much fun. So ultrasonic welding is a very nice way of making waterproof casings. I'm just going to make a basic casing here that we can weld ultrasonically. Top part, bottom part. And then on one of the parts, I make a little plastic bead that goes around. Let's say this is a round thing, right? It has little edge that goes around on the top. And then I put this into a rig, which has a base. That's just like a big piece of metal, like super steady. So you place this into the metal base. That is super steady, right? And then I have a top part of the rig, which is also a metal thing, which is super solid. But this thing has a little ultrasonic driver on it, which sounds really cool, but what it does is it sort of makes it shake back and forth like that. So ultrasonic means like I use sound. I take the 2 parts next to each other and I do this, right? And what happens when I do that? is that this little ring of plastic is going to melt. It's going to be super warm and it's going to melt, and the two parts will sort of be fused together, right? So it's like they're welded together. That's a really quick process. It's like takes a few seconds. It says like beep, and then the parts are welded and they are waterproof. It's super nice, but it's not serviceable. Like you cannot open anything that's ultrasonic welded big because this is effectively like one piece of plastic after you're done, right? But you will often see this on like not air tags, but like similar products to air tags, which are designed to be waterproof. But I mean, by the time the battery dies, the thing is garbage essentially, so it's not service friendly. But that's ultrasonic welding. It's good for some things. Yeah. Next little trick that you can see on cheap electronics. I'm not saying you should do it, but you should know about it. Let's say I got a circuit board like this. One way of attaching this, let's say I got a box like that. That's my plastic box with walls on it. Yeah. Then I can use little towers that protrude this circuit board like that. And if I want to assemble this real quick, I can use a hot air gun. And then I can sort of blow heat on that thing. And that tower is going to melt and create a little sort of donut shape like that. And that's going to keep my PCB in place. It's fairly cheap. It's not very good. Like it's not service friendly because it's going to break if you take it off. Sometimes you can make this and then you can accompany it by a screw tower where you insert no screws. But if someone does service, they can use that screw tower for putting screws and getting the parts together. But that's something you will see on cheap electronics sometimes. It's like, it's a fair way of doing things, but it's not a good way of doing things. Yeah. Yeah. Snaps, good snaps are really hard to make. What you should know about snaps is that it's better to have a snap that has a long travel, like a big overlap, and travels further than to have a small and a hard snap, right? This is, what you see here is a very basic and simple snap. It's not a very good snap. The way to make a good snap is to make the entire wall of something flex, like make the entire geometry flex to make the snap go in and out, okay? So if I'm going to draw my snaps again. That's a fair snap. It's not a good snap. Let's say this was on a product that's like this. If I use, let's say I have a rim or something like, it's kind of hard to, yeah, maybe this is like a box like that. If I can use this entire side of the wall to move in and out, right? Not just like the snap tower like this, but if I can make it move like the entire thing moves, right? This moves quite a bit. I can now put snaps on this, and I can use the shape to make the snaps engage, right? It's a lot better to have something that deforms and have the entire shape deform and use that to make the snaps than to have a little snap tower that does this, right? You can see it on this battery pack actually. Has it. It's really hard to take off, but on this thing, I'm using the entire side wall to sort of flex and let the snaps engage. That's good practice. Snap towers like the one you see here is like, it works, but it's not like nice design. No one's going to give you the Nobel Prize in plastics engineering for this. So try and make the entire thing, the entire shape should flex to leave your snaps going. Otherwise, this will just like, this is very likely to break off. It's just good enough for this application. There's another thing I also mentioned here is that's the angle of the snap. So when you do a snap, if it's a permanent snap, then you should have like any angle between 90 degrees. Obviously that's going to be permanent. But it could also go up to like, say, like that. That's also fairly permanent. If this goes to like anything like this, that's the snap that you can pull apart. This is something you can experiment with. So like anything 0 to 30 degrees, depending on how you measure, like 0 is actually 90 here. That's permanent. If it goes up and gets like more even, then it's not permanent. Yeah. Annular snap, I'm not going to show. Yeah, you can have a look at this raisin box. That's an annular snap. It's the same thing you find on the Kinder eggs. You can do the same geometry on the printer, and it's going to snap very nicely together. Yeah. I'm just going to speed up now so we get a break. Parting line, like everywhere where you have two halves of the mold that meet. Where's the big bulky? Here we go. This one. Yeah. You will get parting lines. That's the part where the parts of the tool meet, right? So on this, like your parting line will sort of be top, bottom, and also you will have parting lines to the inserts. Parting lines are ugly, so try and hide them so that you don't see them, right? Yeah, avoid parting lines on visible surfaces. Also, there's a little trick. If you do, let's say I do my box again, right? So that's a box. If I want this radius down here, like there's a radius on the bottom here. I need to lift my parting line so that this part of the radius is on the bottom tool and that's on the top. If I just let my parting go down at the base, I'm going to get a very sharp corner here, right? So you need to make sure that if you want fillets like next to the area where you have two halves of the tool meeting, like if you want a little fillet here, that also means you need to lift your parting line up like that. We talked about that cord cut. That's making the hole. This is my last slide. Second last slide, promise. Yeah, so your process when you do stuff. One is you make the overall shape, right? Second, you add the detail. And then you start working with your drafts, okay? So don't do drafts in the very beginning. You might do like drafts on the overall shape, but don't draft every detail at the beginning because it's a pain having to work with stuff that's not perpendicular to each other, right? So add drafts. That's like one of the final steps you do is like drafts, and then fillets. That means rounding off the corners, and then mirror your part in the end. So on the side here you can see a box. So what I did, I made a quarter. I did a shell operation. I added drafts, I added fillets, and then I did 2 mirror operations to end up with this, right? That's an efficient CAD process. Okay? Yeah, and if you want to look at like prototype costs, Materialize is very good. They got this online quote thingy. I think Protomol also does it. Don't ask for manual quotes if you just do student projects because people spend time like processing your quotes. But it's perfectly okay to try out these services and just do the online quotes to get some idea of what things will cost in production. Okay? And you're done. Great. Did you guys learn something? Was it okay? Yeah. How about we do a break till 10 past, so that's 10:40. Yeah.